So traditionally, the fourth talk in the series is the most confusing. I'm trying to maintain the tradition. I believe in traditions. Okay, so so the initial talk, we talked about rational polygons and mentioned the, or motivated the question of counting families of closed orbits according to length. And we saw that the problem of sort of using this a version of renormalization, of course, only one technique in dynamics, which is renormalization, but it comes in many flavors. Okay, so we're looking at our particular flavor of renormalization, and in our case, this involved translating questions from the straight line flow on a translation surface to questions involving this SL2R dynamics on a space or a moduli space of translation surfaces. So if I use the term moduli space, I just mean some family of geometric objects, okay, not necessarily family of Riemann surfaces, but we have a so we're translating from a sort of one type of a dynamics on a surface to a dynamics on a space of surfaces, right? That's what our renormalization does for us. So you can ask here, I mean, we're starting with problems with a certain flavor on the surface, and then we're replacing those by different dynamical problems. You can ask, is there some connection between the original problem and the new problem that we've come up with? They're certainly not the same. They're acting on different spaces. But I think you can see in many cases there's some kind of correspondence principle that's relating these two different settings. It's not a theorem. It's not quite a philosophy, but in various places you can see some kinds of correspondences. For example, the case of the torus. This is in the case of the torus. So example of correspondence principle. The torus T2 versus the moduli space SL, the moduli space H10 equal SL2R mod SL2Z. And the correspondence, let me be more specific, and here it involves the straight line flow. And here I want to specifically look at the Horocycle flow. Okay, so it's not the only flow not the only flow that we've been discussing, but this is where I want to suggest that there's some kind of correspondence between the two situations. Okay, so if we so the torus corresponds to this, right? So if we consider T2 here, so we've identified opposite sides, then what's the story for the straight line flow? Dynamically, orbits, let's see, orbits are either closed or dense. In other words, orbit closures are either single trajectories, well, whatever, let's close that up. If you're traveling in a rational direction, or they're dense if you're traveling in an irrational direction. So there's just two kinds of orbit closures, hints. There's also just two kinds of invariant measures for the straight line flow, really. There's invariant measure, or two kinds of ergodic invariant measures. There's ergodic invariant measures on closed orbits, and there's the sort of the Haar measure for the torus, right? Or either closed or dense, and well, in any case, there's a close connection between the topological dynamics and the measure theoretic dynamics in this setting. Well, what about this case? H sub t acting on H1, 0. So H1, 0, right, this is the unit tangent, as we've seen, this is the unit tangent bundle of this hyperbolic surface. And what are the types of horocycle flows? Well, it's very similar. There are two types of orbit closures in this setting. There's the horocycles that they're closed horocycles. So those are horocycles that are traveling around the cusp. Okay? Or the other type of horocycle, or it's either that's one type, and the other type of horocycle is dense. I mean, either the horocycle is closed or dense. Okay, so the orbit closures are right, very so orbit closures are closed. I mean, orbit closures are periodic or everything. Okay, so yeah. No, the horocycles, Barak showed that horocycle orbits are non-divergent, which means that the amount of time they spend in the cusp is proportional to the size of the cusp. It doesn't mean they avoid the cusp. It means they don't overstay their welcome in the cusp. They're not spending too much time in the cusp. Okay? So they're uniformly distributed, right? Ergodic invariant measures are either supported on closed orbits or Haar measure. Okay, so yeah.
Is it a general fact that an ergodic measure is a limit along some trajectory?
Yeah.
That's always the case in any dynamics.
Typically, yeah. So let's see. So the case of the torus is the only case. I mean, the genus 1 case is the only case in which the strata is actually a homogeneous space, and there's kind of an analogous picture in homogeneous spaces too. There's a kind of analogous correspondence principle in homogeneous spaces. So if if we consider instead of SL2R, if we consider the space of n tori, En, again, if you look at, there's again a correspondence principle between, so on the one hand, versus straight line flow on tori. So space of n tori, and here I want to, okay. Let's see. On the one hand, I want to compare the space of n tori, unipotent flow, on the other hand, versus the torus itself and the straight line flow. Okay, so again, there's a very, in this case, there's a very surprising correspondence. Orbit closures here are all translates of subgroups. So they're translates of sort of essentially linear subgroups. Orbit closures over here, again, are closely related to subgroups. They all have a kind of algebraic structure. And this, in this case, this relationship, or the fact that, that orbits are well behaved on this side of the picture is referred to as Ratner theory often. Often and incorrectly, because it's the work of many people, but let me just follow this incorrect terminology with the caveat that I know it's wrong and you know it's wrong, but we'll just, okay. It's convenient. It's convenient. Pardon?
Wrongs maybe, let's say oversimplified.
Yeah, fine, fine. Okay. Okay, so, okay. So then the next question maybe is what happens. Okay, so this is what happens when we go from T2 to Tn, right? We take our torus, raise the dimension. Well, we can also take our torus, raise the genus. So we can ask over here what happens for translation surfaces of higher genus. Okay, so so translation surfaces of higher genus. Okay, so we know we have examples of closed orbits. We have example of dense orbits. Let me say that there are non-closed orbits which are not dense. Okay, so this is, yes, okay, in the higher genus setting, in particular in genus 2. One way to construct such a thing is to glue two tori together along a slit and choose the slit to be in an irrational direction. Okay, then consider an orbit on one of those tori, which is traveling in this irrational direction, okay, but doesn't actually hit the slit, right? It's easy to miss, okay? So that orbit remains in this torus. It's not crossing the slit because it's parallel to the slit, and its orbit closure will be just one of these two tori. Okay, so that's a general pattern. So Sasha mentioned this question, and connection with Keen's theorem in interval exchanges, but it's a general phenomenon that orbit closures in surfaces, translated surfaces of higher genus can be subsurfaces with boundary. And that's all that can happen. So it's not exactly like the torus, but it's not wildly different. You're going from manifolds to manifolds with boundary. Okay, let me just show you. So let me, here's. Okay, they're non-closed, which are dense, and there are dense orbits which are not uniformly distributed. Okay, again, in something more complicated, and let me show you. So I want to look at a particular polygon that leads to this two torus situation. Okay, so so the polygon I'm looking at is really just this slit rectangle. This picture has two things in it. So I'm starting with this rectangle with a slit. Okay, maybe not literally a polygon, but we're sending trajectories that when they hit the slit, they bounce off the slit. Okay, so it's essentially a polygon. We can still build a translation surface from this, and the translation surface is exactly these two tori glued along a slit. And in this particular picture, I've drawn a billiard orbit that starts at the end of the slit. I mean, not the slit, the barrier starts at the end of the barrier, comes back to the end of the barrier. And this trajectory really corresponds to a slit in one of the tori. Okay, so it's not a closed trajectory, but it corresponds to a slit. So and it corresponds to a slit with irrational direction. So if I pick an arbitrary starting point, let's see what we get. Yeah, so it will lie in one of these tori. Okay, so here's an example of an orbit which is not periodic, but not everything. Okay? Okay. We can build on this example to create this second phenomena, orbits which are dense but not uniformly distributed. Okay? So in this table, I want to construct an orbit that fills up the table but spends more time on the right-hand side than the left-hand side. Okay? So that's the uniformly distributed orbits will spend the same amount of time on both sides. Okay, so what I want to do is take this sort of slit picture and modify it a little bit in a suggestive way. Okay, so here what I've done is I've taken a much longer slit where you can see that in terms it's denser. It's denser, but it still has the property that it's spending more time on the right-hand side than the left. If you consider this kind of continue this approximation procedure, you can get something which is genuinely dense, but has this property of spending more time on the right than the left. Okay? So that's a new phenomenon in the higher genus setting, which doesn't happen in the genus 1 setting. Yeah?
What were the constraints on the length of the slit?
What do you mean? Oh, you mean, well, no, the slits can be arbitrarily long. Okay, slits can be arbitrary.
Any slit length you construct.
No, you have to do this carefully. Okay. Don't try this at home. This is, these slits have been constructed by professionals. And the success of slits, and indeed this is a very delicate phenomenon. It does not happen for a typical direction. It's a very delicate phenomenon, but it can happen. That's what I'm saying. Okay? So, I mean, in fact, I'm claiming there's a sequence of, I can find a sequence of slits, so this becomes denser and denser, and then that limit will have this required property. Yeah. It's a kind of an approximation argument. I've just shown you 2 steps in the approximation.
Is it a sequence of directions?
What's that?
Isn't it a sequence of directions? I mean, the directions?
Yes, these directions, I'm fixing the table and the directions will be changing slightly. But I want, in the end, the directions will converge to some direction.
But the slits would always be the same, I guess.
No, the slit is not, no. So this, the barrier is not the slit. The barrier will always be the same. Is that, am I being confusing on that point?
The slit is this vertical thing.
No,
That's the barrier.
that's the barrier. The slit is some particular decomposition. I've got, well, okay, let me say this again. I've got 2 tori joined along a slit, but they can be presented as 2 tori joined along a slit in infinitely many different ways. Okay, so I'm choosing different ways of presenting it as 2 tori joined along a slit, where that slit is getting longer and longer. Okay, but it's the same surface. Okay, I'm just choosing different presentations, changing my trajectory direction appropriately.
So we are talking about different things here, because in this picture, this is only the billiard table. But when we are seeing slit, we are seeing translation surface.
Yeah, that's right.
So we should unfolding this billiard table into the translation surface.
No, you should unfold it into a translation surface. I should assign this to you to do as an exercise. Yeah, but that's right. I'm drawing to really start to understand what's going on. It would be clearer to draw the translation surface. I'm just giving you the snappy summary picture. But, yeah.
You mean that if we have barrier, then we will have slit? Do you mean this?
No, it's part of the homework. I'm not giving too many hints. Okay, but I think it's in there's 2 sets of homework problems online, and I think maybe this is in the first set of problems. The ones come from me. There's also problems from Barak, but it's one of the homework problems. Okay, so let me go back. Okay, so then the natural question to ask here, is, well, what goes on? What's the analogous behavior for horocycle flows in strata in the higher genus case, right? Okay, and that's kind of topic topic that I want to continue with. Okay, so Barak in his lectures gave examples of various SL2R invariant sets. In fact, this example is contained in, so if we call this polygon P and this surface M sub P, then M sub P is contained in this eigenform locus E4 that Barak mentioned. Okay. 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 And that's an example of an SL2R invariant locus inside H11. Okay. So Barak gave various examples of horocycle invariant measures, ergodic horocycle invariant measures inside H11. So yeah, so what I want to do now is kind of resume the thread of the kind of renormalization analysis, and we'll come back to this sort of correspondence principle at the end. Okay, so I've left out of this correspondence principle what's the analogous behavior for the horocycle flow in, for example, H11 or eigenform loci E sub D, and we'll come back to that at the end. Okay, so so let's see. So now let me just review review our discussion. Okay, so I want to return to the counting problem. So maybe I'll just send this board up. Okay, so okay, so what we did was we start with we have a polygon P, gives rise to a surface M sub P, and we wanted to consider limits of circle measures circles centered at M sub P inside the orbit closure SL2R, inside the SL2R orbit closure SL2R M sub P. Okay, so right, so Barak gave examples of various orbit closures. So for example, these eigenform loci E sub D, or Veitch surfaces, Veitch examples, which include the square-tiled examples. Okay. So Barak showed that the limits of these circle measures well, we don't know what the limits are, but we know they are Horocycle invariant. Furthermore, a priori, there's an issue when we're taking limits of circle measures in a non-compact setting. There's an issue that those limits of ergodic measures, that is, measures that assign total mass 1 to the space, might, well, yeah. So right. In order to be guaranteed that we have convergent subsequences, we need some compactness for the space of measures. In the non-compact setting, we don't have compactness of the space of measures, right? So one thing we could do is, so I'm answering the question, why do limits of subsequences exist? Well, we've got some space. Let me just think of our stratum as something like this, which is definitely not compact. Okay, we could, to cheat, we could just add a point at infinity to our space. Our space is locally compact. We can compactify it by adding a point at infinity. Okay, we could take now sequences of measures converge to measures. So we could take our sequence of circle measures. They have some limit, And we would like to know that this limit measure, they have some limit in this one-point compactification. We'd like to know that that limit measure does not assign any mass to the point at infinity. Okay, so that's exactly what Barak proved in his third lecture, I believe. The uniform non-divergence, well, it's not exactly what Barak proved, but it's essentially what Barak proved. Barak showed a uniform non-divergence result for Horocycle orbits, but that same uniform non-divergence applies to large circles, because we know that large circles are very close to horocycles. Okay, so so we can choose a convergent subsequence and according to uniform non-divergence, the limit assigns measure 0 to the point at infinity. Okay, so we have as a result a genuine probability measure which is Horocycle invariant. Yes, Chris.
Why are the circles? So here the circles they're defined by the rotation.
Mm-hmm.
Why you say they are close to the circles given by the Horocycle flow?
So I think Barak showed that limits of circle measures are Horocycle invariant. Okay, Horocycle invariant, yeah. So, but just, I don't know, I've forgotten whether Barak drew the picture. Okay, so the picture is that if you have well, so this is this is what a very large circle looks like, okay? This is what a horocycle looks like. They're very close. Okay? I mean, both geometrically are circles. One's a circle in the interior of the disk. The other is a circle tangent to the boundary.
But the thing is, the center of the circle is fixed. Okay? So it's not going to the boundary. I agree that if you take a sequence of circles whose center is going to the boundary, then it's going to look like a Horocycle. Because the center is fixed, so we can pretend it's the middle of the.
But by drawing the sort of the universal cover, the disk picture, I'm cheating a little bit because this is really a phenomenon that only makes sense inside the moduli space, right? So inside the moduli space, you really have to think of a family of circles based at all the different orbits of this particular point corresponding to this particular surface. So think of a family of orbits filling out, and whatever it will be true in the limit that you get a measure which is Horocycle invariant. Okay.
In this picture, if the side in the down tends to the boundary, but also the upper bound, the side also will tend to the boundary. So you do not get a horocycle. You get this.
I'm not claiming I'm proving this to you. I'm claiming that Barak proved this to you, and I'm just drawing the picture. So Barak may have not drawn the picture because it adds to the confusion. He just left that to me. But in any case, I'm drawing the picture. Okay, so this Barak both proved this and he's written up notes. So let me just refer you to those. And then if that's not satisfactory, you know who to go to track down the result. Okay, but so I want to return here to the philosophy, the counting philosophy. Okay. So the counting philosophy is that we want to show, according, Right. Let's see. So according to Eskin, Mirzakhani, Mohammadi, there is a sort of natural probability measure nu on this orbit closure, which kind of plays the role of the Haar measure. It's kind of a full dimensional, it's a smooth measure on this space, which is a manifold. And what we want to do is show that our circle measures converge to this particular measure nu. Okay? In the case of the full stratum, this is the famous Maser-Veitch measure. Okay? But in other cases, it might be a different measure. Right? So that's our philosophy. We want to show convergence to nu. Okay, so what do we have to do here? So we've got convergence to something. It's Horocycle invariant. What's the next step? Classify Horocycle invariant measures. Okay, so we classify Horocycle invariant measures. So we have this measure nu because it's SL2R invariant. As Barak explained, it's also horocycle invariant and ergodic for the horocycle flow because it's ergodic for the SL2R action. So let's see, classify ergodic horocycle invariant probability measures. So nu is on our list, and then we've got a collection of other measures. Okay, so the trick then is to analyze the remaining measures and show they cannot be circle limits. Okay. If we've done that, then we only have one candidate left, which is nu, so we know we're actually converging to nu. Okay, it's a standard kind of sneaky homogeneous dynamics, typical homogeneous dynamics argument. Well, sneaky but powerful homogeneous dynamics argument. It's kind of indirect. Okay. How are we doing for time here? What's my pardon?
5 after 10.
Oh, okay, okay. Let me just mention that there is, well, to see, okay, I don't really have time for this, but to show that certain things, measures can't be circle limits, let me say here that Barak almost gave this argument in his, just in the special case of SL2R mod SL2Z, Barak almost gave that argument. And I'm just going to draw the pictures that we need to complete Barak's argument. So, so this would be an example. Well, let me see. I think, okay. Maybe I'll bring down the board. So, So a test, so an example, in SL2R, or I'm sorry, keeping with our notation here, in H sub 1 of 0. So we know there's two kinds of measures. There are these measures on closed orbits, or there's the Haar measure. The nu here is the Haar measure. So we want to show that no limit of large circles can put positive mass on the union of the closed orbits. Okay, so circle measures. I mean, we didn't want to show this. We want to claim that Barak has already shown this to you. Puts positive mass on union, the union of circle orbits. Okay, so this comes down to this picture that Barak drew. So we have this sort of box of size 1/2. We have here a box of size epsilon inside it, right? And this, yeah.
Are we talking about orbits of the Horocycle?
I'm going to talk about orbits. Well, large circles are essentially horocycles. Okay, so
In this statement, circle orbits of what?
no limits of circle measures put positive mass on the union of the union of closed horocycle orbits is what I meant. Okay,
Horocycle orbits.
closed horocycle.
Those horocycles become the whole thing.
So closed horocycle orbits, those are candidate measures, but also Haar measure is also a candidate measure.
I mean, the union of these horocycles covers everything, doesn't it?
No, it's not. It's dense, but it's not everything. Right? So if you take a closed horocycle and you push it down, it gets longer and longer. So you're getting a one-parameter family of closed horocycles, but it's a one-parameter family of closed horocycles inside a three-dimensional manifold. It's dense, but it's not everything. All right? The question still makes sense. Okay? So we want to show that. Well, so in this picture, right? This picture corresponded to the, say, the coordinates of the shortest. So the coordinates of one of the basis vectors of the torus, and the key point was that in the box of radius 1/2, you can't have two basis vectors of the lattice, both with coordinates inside this box. Okay? Okay, so he showed that the amount of time that you spend inside this little box is at most 2 epsilon. And that's true for any limit of circle measure. You spend at most 2 epsilon inside that box. We've got some segment over here, and we want to show that the amount of time you spend close to that segment is small. Okay? So what do? We just apply the geodesic flow to this box. In other words, we shrink it this way, expand it this way. And we do it. We do it so much that the epsilon box now covers this red set. Okay? Performing this translation of the box gives us another box with the same property, that we can only have one basis vector for the torus inside this box. Check that. And this Barak's argument tells us we can spend at most epsilon of our time close to this union of closed orbits. Okay, so let epsilon go to 0, and we can't. We see that we can't be spending any time. We can't be spending a definite percentage of our time close to the union of closed orbits. Either that was very clear or it was very confusing. I'm guessing the latter, but I'd like to finish up, however. I'd like to have done that better. I didn't. Let's move on. Okay. Okay. So right. So that's the I've reviewed the philosophy. Okay. So we've reviewed the philosophy. I established a connection with many of the things Barak said. There's one more ingredient here, which is one general ingredient in this analysis of analysis, this kind of Ratner type analysis of the Horocycle flow, which is sort of normalizers of the Horocycle flow. So in the homogeneous world, everything is translated into group theoretic language. So normalizers and centralizers of the Horocycle flow. What does that mean? So an example of something that normalizes the Horocycle flow is the geodesic flow. Note that the geodesic flow takes closed orbits to closed orbits of different length, but it takes closed orbits to closed orbits. So in general, something in the normalizer will take a Horocycle invariant orbit to a different Horocycle invariant measure or orbit to a different, say, Horocycle invariant measure to a different Horocycle invariant measure. Okay, keeping that picture in mind. So check that if gamma commutes with h sub t and x is h sub t invariant, then gamma of x is h sub t invariant. Okay, so this gives us a strategy for creating new invariant measures from, in particular, SL2R invariant measures are Horocycle invariant. But if we can find, say, commutators of the Horocycle flow, things that commute with the Horocycle flow, we can apply those to SL2R invariant measures and get new invariant measures. Okay, so and then all right, so so this is the regular decagon, and we can deform the so this is the regular decagon, or covering the surface. Yeah, this is the regular decagon. We can deform the regular decagon by moving. So it's in H11. It has vertices of two different types. We can deform it by moving all the white vertices in a particular direction. Okay, so we get now an irregular decagon. If we do this deformation in the horizontal direction, we get a flow on the space of translation surfaces. And if we choose to do it in the horizontal direction, we get a flow that commutes with the Horocycle flow. Okay, so this is called the real-rel flow. Okay, so this gives us a way of taking invariant measures, creating new invariant measures. Okay, so for example, the decagon locus, the decagon is an example of a Veitch surface. Its locus is closed inside H11. So so there's a measure supported on the decagon locus. So we can apply real-rel to the decagon locus. Decagon locus, I mean the SL2R orbit. In this case, it's already closed. We don't need to take the closure. Okay, so we get a new invariant measure. interestingly enough, this is an invariant vector field which is not defined for all time. So if we do this in the horizontal direction here, if we let me move the white points in the horizontal direction, and the or let me move what the let me do this. This is moving all points of the same type in the same direction. So this is just a bit. If we perform this real-rel operation to the decagon, you see that points collide. So we've got an example of a flow which can't be defined for all time. So if we apply this to the decagon, apply this real-rel to the decagon locus, we get some kind of tearing phenomenon, which gives us an orbit closure, which is gives an orbit closure, which is a manifold with boundary. Okay, so it's a little bit different from the homogeneous world, but eerily reminiscent of the setting of genus to surfaces and the vertical flow, right? So, so rel, I'll write this flow as rel sub t of the decagon locus is a manifold with boundary. A simpler picture to imagine here is if we just think about a picture to imagine which captures the key properties of what's going on. If we just think about the billiard flow at a singular point, like this, right? The billiard flow is itself discontinuous, right? So if we take something like that, apply the billiard flow, we get some kind of tearing here of this locus, and the result gives us a manifold with boundary. Okay, so so these applying the real-rel flow to the examples that Barak has already mentioned gives us additional examples of Horocycle invariant measures. It gives us all so it gives us all the Horocycle invariant measures in eigenform loci. So and then right, we get all the eigenform, all the Horocycle invariant measures in eigenform loci. We apply this argument that no one really understands, and it rules out the extraneous measures and tells us that circle measures are actually converging to the sort of the Haar measure in the eigenform case, and that completes the program for translation surfaces, which are it completes the counting program for translation surfaces which are actually contained in eigenform loci. So, for example, the translation surfaces corresponding to these tables and this is 1, 1, 1, 1, T. So this is the slit billiard we talked about before. So we get n sub L in this case is equal to C times L squared over area squared with C equal 9 pi over 8. In this case, we get the same fact with C equal to 15 over 2 pi. Okay, so we can actually complete this counting program in certain settings. This condition here assures us that the corresponding table is inside an eigenform locus, right? That's where our arguments work. Okay? You can ask, well, what happens if you're outside of the eigenform locus, it may be in H11 but not in the eigenform locus, do your arguments still succeed? And the answer is we don't know. But we don't know what happens in general. But we know there's some weird things that are going on. And one of those weird things, we know that there's some, one of those weird things is what we call the spiky fish. So let me just explain. What am I talking about? Oh, so let me bring down the, is that? Okay, so weird behavior for Horocycle orbit closures in H11. Okay, and so this is joint work with John Chaika and Barak Weiss. And what we, John Chaika has been giving talks about this, as has Barak. John Chaika forgot to show the photograph, okay, the spiky fish photograph. So I'm trying to redress this issue here. So what's going on here? So in this, as perhaps you can tell, in the picture, the fish is this locus E4. Okay, and what we've done is we've taken some surface inside E4 with a non-ergodic horizontal foliation. Okay, so that's exactly this kind of behavior that corresponds to orbits that are dense but not uniformly distributed. Okay, then so if we think about that sort of in, okay, so we can kind of build this surface out of charts, and on each of these transversals, we've got some measure nu sub 1 here, which is not the Haar measure, but some other measure, some invariant measure. Okay, well, channeling Alex's lecture, what do? We just use that measure to do some kind of shearing, right? Which, it's like an earthquake, but it's simpler than an earthquake. Because we can actually write down a formula for how this shearing works. In the earthquake, you have to worry about the directions of these lines and how far you're moving along a given geodesic. And the lines are controlled, but here the lines are all in the same direction. And the amount that you move, so the picture is you're taking this, so we're using the term trimmer here. The trimmer takes this and shifts it to the right, shifts points to the right by an amount which is based on the nu sub 1 integral of this segment, right? It's a transverse measure. So we're shifting to the right by, if we were using the Lebesgue measure here, we would get the Horocycle flow. We're not using the Lebesgue measure, we get something that commutes with the Horocycle flow. So we get some kind of something that an operation that commutes on E4, which commutes with the Horocycle flow, that allows us to push points from E4. It's only defined on these translation surfaces with the trimmer is only defined when the horizontal foliation is not uniquely ergodic. That's a set of measures 0 inside E4. So we've got some kind of push that we're doing on a set of very small, 0 measure. So it's changing the orbit but it's not really changing the measure, right? It's not pushing the measure, but it's pushing the orbit. So it gives us a very strange orbit closure. So inside this picture, the fish is E4, and the spikes represent surfaces with non-ergodic horizontal foliation, which have gotten pushed by the trimmer. Okay, so it's somewhat, well, I mean, you can imagine pushing by the trimmer, but, and that gives you certain, those are the spikes, the pushes, but maybe the surprising thing is that even after doing all those spikes, there is some point whose orbit closure is the whole spiky fish. Okay, so this is an orbit closure of a single orbit. Okay, that's the surprising thing. Okay, this is sort of the last, maybe this is the last piece of this correspondence principle, right? We needed to find, maybe, you know, we're looking for strange phenomena associated with related sort of manifolds with boundary. We found those. Looking at strange phenomena associated with non-unique ergodicity. Maybe we found it. We don't know. So the conclusion is that there are some powerful techniques, sort of applying Ratner-type ideas, give us some powerful results, but the project is far from done. Very interesting, open directions to get a kind of thorough analysis of all strata, and we're just in the beginning of that process. Let me stop there.